So we're going to take the basics of alkane nomenclature and we're just going to add some additional information on. So this doesn't change any of the rules as before. It just allows us to analyze and name more complex molecules. So cyclic alkanes are going to be those ones bonded in a ring and they follow generally the same rules. You're going to count that was my dog, if you could hear that. So you're going to count the number of carbons and then you're going to apply that same prefix. So the prefixes are the same as before with our straight chains. But then the prefix gets a prefix of cyclo, and that becomes the parent chain, and you add ane on the end. So we can do this with small rings. So for example, here's a 3-carbon ring. It gets the 3 prefix of prop, and then cyclo added on the front, ane on the end. 4-carbon ring gets bute, gets cyclo, gets ane, and this can work for any size ring of carbons. Now, most common being the cyclohexane that we see in that hexagonal shape, and cyclopentane is pretty common, but it does work for any of those prefixes. So generally the same rules for cyclic alkanes as there are for normal alkanes. This is key. The ring is almost always the parent chain, and it doesn't include any carbons that are on substituents in the same way that we don't include the ring carbons in the substituents. The only exception is going to be if there's an alkyl chain that doesn't include any carbons from the ring that's longer than the ring itself. So let me give you an example of one of these exceptions. For example, if my molecule was like this, and I had a 3-membered ring coming off, you would honestly use the same naming conventions as before. So my parent chain here is 1, 2, 3, 4, 5 is pentane. Okay, this is cyclopropyl. We add the YL on the end. So this would just be called 2-cyclopropyl pentane. That's the only time you're going to get an exception. Very, very rare. Just wanted to show it to you. So if there's only one substituent on the ring, you don't need to put a 1 when naming it because it's just assumed to be in the first spot, right? The cool thing about rings is you get to pick wherever you want to be carbon number 1. And so if we only have one substituent, we're always trying to number for the lowest possible numbers. So that one substituent is obviously on carbon 1. But if you have multiple substituents, you're going to number for the lowest possible combination of numbers, and all those same rules still apply. If all things are the same, we prioritize halogens, and if all things are still the same, we prioritize the alphabet. So really, it's not that many new rules, just a little bit different. We're going to do some practice in a minute. But first, we're going to talk about some other special types of names. So the type of naming that we've been talking about is called part of the IUPAC system. It's this international organization that sets all these complicated rules for naming compounds so that it's uniform internationally. They're sometimes called the systematic names. They follow this set of rules. But there are some really common types of substituents that aren't necessarily straight lines like ethyl or propyl, but they're used frequently, and so they get these common names assigned to them. And a molecule can have both common and an IUPAC name, but you should know how to name with some of these common prefixes or substituents because they do show up often. So here are the 4 prefixes you're going to want to know. We're going to go through them one by one. We can have iso, sec, tert, and then neo, less common but still common. Something that can get a little confusing is that sec and tert prefixes do not count towards the alphabetical ordering when we start to name something, but iso and neo do. You can always see that distinction because when sec and tert are used, they will always have a dash, and if they're typed, they're usually in italics, whereas iso and neo will not have the dash. So that tells you that iso and neo now sort of count as part of the prefix or as part of the substituent name, and they get counted in the alphabetizing, whereas sec and tert do not. So let's look at these one at a time. The first special one, and probably the most common, is the iso group. It looks like this. It's a little bit harder to see when written in condensed. It's pretty distinctive when it's written in a line bond structure. It has sort of this distinct sort of V shape from our substituent, and this R group would be most often your parent chain, right? So that can be used as a substituent. But we can use this name as either a substituent or a whole molecule itself. So here's an example of it being used for a whole molecule. Isobutane, where I have this V shape, so that's the iso, and I have 1, 2, 3, 4 carbons, so that's where the butane comes from. Isopentane, again, the V shape, this time with 5 carbons, but it can also be used as a substituent very commonly, where I see the arrangement of the atoms like this, and the substituent has 1, 2, 3 carbons in it that are not part of the parent chain, so that's where the probe comes from, and the parent chain is heptane. Again, same nomenclature rules when it's used as a substituent, and in this case, the I in iso would count towards alphabetizing if there were other substituents. Next, we have sec and tert. These names are not random. They're short for secondary and tertiary, and a secondary carbon is one with 2 other carbons bonded to it, and a tertiary carbon is one with 3 other carbons bonded to it. Generally, these are used only for substituents. So here's what they look like. Again, harder to distinguish when written in this condensed format, a little bit easier when written in line bond. I think the sec one looks like kind of a bowl of soup, but it can also be drawn in more of a zigzag format like this. That's the same thing. It's secondary because this, the start of my substituent, has 2 carbons bonded to it. This is tert. It's often referred to as a little chicken foot, different than the iso because it's got 3 branches as opposed to that V shape. And so that's what tert most commonly looks like. The last one being neo, much less commonly used. Simplest molecules are often named this way. It's the simplest 4-carbon molecule that looks like this. It can be used as a substituent, but again, is much less common, so I would worry about those other ones first. All right, so let's do a little bit of practice combining both of our common naming system and the new cyclo naming system that we have. So I can see in this first example on the far left, I have a cyclo group. It has 1, 2, 3, 4, 5, 6 carbons in it. And so the end of my name has to include hexane for 6. And then because it's a ring, it's going to be cyclohexane. Now I started numbering it at this substituent because your number 1 carbon should always have a substituent on it. But now I need to see, should I number the other way? Should I start 1 here and go this way? When you do that, you actually notice that the red and the blue naming system end up with your substituents on the exact same carbon, and so it doesn't actually matter. This substituent here is 1 carbon because remember we don't count the carbon in the parent chain, in this case the ring. That makes this methyl. And same here, also 1 carbon, so that makes this methyl as well. Okay, so I'm going to need a prefix. That prefix will be di, and I need the 2 numbers in the front. So it would be, to finish out this name, 1, 3 dimethyl cyclohexane. And I could start carbon 1 no matter where I want. If I want to make this carbon 1, that's fine. This would be carbon 3. And if I just like rotated this molecule around, you'd see that it would be the same. So it doesn't matter where you start your numbering, as long as you have the lowest possible combinations of numbers for substituents. All right, looking at this one in the center, this is not a cyclo compound, so I don't need to worry about any of that, but I do see this substituent here, and that substituent is one of our special substituents. That's a tert substituent. There we go, and it has 1, 2, 3, 4 carbons in it, so that means this would be called a tert butyl substituent. All right, now I need to look at my parent chain, make sure I number it from the lowest possible direction for my substituent. So it looks like if I start on the right here, I'm actually going to get the lower number for my substituent, but I'll double check in a minute. So I've got 10 carbons. Right now my substituent on carbon 5. If I started here, 1, 2, 3, 4, 5, 6, it would be on carbon 6. So the blue numbering I wrote out is correct. All right, so my name would be 5 dash, and you do get 2 dashes here. I get a dash for the number and then a dash for the tert, and then butyl, and then the prefix for 10 is decane. Again, if I had more than one substituent here, this tert would not count for the alphabetizing. I would have a B substituent there, and we'll get more practice with complicated ones in class. All right, last one. This is a cyclo compound with 1 substituent on it. So that's always going to be carbon 1. Doesn't matter which way I go around because I have no other substituents. 2, 3, 4, 5, 6, 7, 8. So the prefix for 8 is oct. It's going to be octane, and it's going to be cyclooctane. Then I look at this substituent here. This is also a special substituent. This is my sec substituent. So this is sec, and then I count 1, 2, 3, 4. So this is going to be sec butyl. Because there's only one substituent, I don't actually need the name or the number in my name because it's always going to be assumed on carbon 1. They're always going to assume that you numbered it correctly. So this would just be called sec-butyl cyclooctane. So those are some pretty straightforward examples. We'll get through more complicated ones where we combine multiple substituents, etc. But just a quick little addition of some extra alkane nomenclature rules for more complex compounds.